Hi to all, I hope you're all doing really well. This video tutorial is part of the CNC series and in this video I would like to show you how I modeled in context the Z-axis frame using as a reference the components subassembly assembled with the assembly3 workbench from Real Thunder. Before we start, I'm using FreeCAD LinkStage3 release 0407 from Real Thunder, and you can download it from this GitHub page. And if you like how my interface is customized, I've made a video tutorial that you can also find on this channel. So with this out of the way, let's get straight to work. So the ultimate goal for this tutorial is to design and assemble the Z-axis for this machine, but always keeping in mind that the design is in context and that it needs to reference the attachment points on the previously built frame. To do this, I will assume that we already have all the various components already modeled. We will make an assembly out of them, and we will use that assembly as a reference for the attachment points that we need on the sheet metal frame design. To have a better understanding of the relationship between various components with this build, we should first take a look at the project structure. So if we go here and we choose Show Multi-Document, it will show us all the files linked in this CNC rebuild top file that contains our main assembly. This main assembly is made by subassemblies, for example the CNC body, that are contained in their own subassembly files, individual files. I know for example that this CNC body subassembly is a link in the CNC body rebuild file, and if we open it, we can see that this file is made of an assembly that contains individual components. For our Z-axis model, we will use the same logic. We will make the assembly of the various components that will be a subassembly, and then we will link everything in the top assembly file that holds our project. If all this seems a bit confusing, just bear with me and you will see that this kind of workflow is really powerful and not at all complicated. So I created a folder where I've put all my individual components files, and we will open them one by one. We have a 3-to-1 pulley assembly, and you can always choose between seeing the multi-document view or the single document one to not get confused. And these are more or less the components that we will need to use in order to assemble our Z-axis. Because I want to model in context, I need the context of my X-axis carriage, and especially these attachment points here. But I can't reference this top level assembly because we will hit the cyclic reference error, and I will explain you why. So imagine that our whole project is a pyramid. At the base of the pyramid we have our various components, and these are, in the case of our project, the various components. These various components can be in individual files or even in the same file, and they can form subassemblies. These subassemblies again can be in their individual files or even in the same file, but by creating links in a top assembly file, we can create a top assembly made by various subassemblies. If, for example, like here, if I go to my CNC rebuild file, if I take a reference on this top assembly file, which is this one, And I'll use it, for example, if this little square here represents our z-axis assembly. If I take a reference in this top assembly and I use it in this sub-assembly, we'll create a cyclic reference dependency error. And this is not permitted in FreeCAD. What we can do is to create our reference horizontally. We can reference the geometry in one of the sub-assemblies that will later go on to build our top assembly. So bear in mind that this geometry that we wanted to reference here in the top assembly is present in one of the sub-assemblies. So to avoid the cyclic reference problem when modeling, always avoid referencing some top assembly geometry, but go horizontally, referencing the geometry in the sub-assemblies that will form the top assembly. Getting back to our file, I want to reference the x-axis carriage, and this x-axis carriage is in this file that I will open. And please don't mind the wrong naming here of the file. It is named as a y-axis carriage rebuild, but it's actually the x-axis carriage. Anyway, now that we've opened the correct assembly of the geometry that we want to reference, we will start to select the geometry that we want to reference, and this is this one, and this one. And by moving into the part design workbench, I will create a SubshapeBinder. I can rename this SubshapeBinder as X carriage reference. Now let's create a new file for our assembly, and we will save this file as z-axis version 2 perhaps. Now with the file saved, what I want to do is to bring in all the components that are needed to build the model. So I will go to this file here, I will choose the pillow block assembly, go back to my z-axis file, and we will make a link. The same with all the other files, so I need the pillow block assembly, and this pillow block, it is an assembly because there is the model and then the screws that form an assembly. The same, go to my z-axis file and make a link. The name of motor, So just to be clear, in order to make a link to an external document, open your document, select the geometry that the body or the part or even the assembly that you want to make a link of. Then go to your file and hit this button to make a link to your external geometry. So with all the components important, it is now time to move to the assembly3 workbench, and we will create a new assembly. If we expand the tree for the assembly, we can see that we have two new entries. One is named parts and one elements. As soon as we will start constraining, a new entry will be created named constraints, and in there will be stored all the constraints and relationships that we will create between elements. For now, let's start by renaming this assembly as z-axis components. To have a cleaner tree, I will create a new folder, rename it as components, and I will drag every component inside it except the assembly. And this way we can toggle the visibility of the components as a group. Inside this z-axis components assembly, the first element that we need to import is actually the reference that we've previously created, named X carriage reference. So I will select in its respective file this SubshapeBinder, go to my z-axis version 2 file, and I will create a link. As you can see, the link was created outside of any container. I will drag my link inside the assembly. Notice how the link was placed under the Part1 branch. In a functional assembly, the first element, the first constraint that we need to add is a locked constraint, and this will create a origin or a locked point for our assembly. In my particular case here, I think that a really good candidate for the start of my assembly could be this face on the SubshapeBinder. I will select it and then select the locked constraint. As you can see, a new entry was created in the tree structure of my z-axis components assembly. This branch is named constraints, and underneath it we'll find the constraint containing the element or the elements that hold the relationship between geometries. In the case of the locked constraints, we have only one element, which is locked in place. And also bear in mind that the constraints have properties that we can tweak, and we will see this at a later moment. Now, with a starting point set it up for our assembly, I will start to bring in the various components that we need. And the first one that I will bring in is this screw. So select the screw link. You can use the TD shortcut on your keyboard to drag the component inside the assembly, and it was placed underneath the Part1 branch. Let's hide all the other ones. Right click, transform, and we will place it roughly where it needs to be. Escape to dismiss the tool. For this particular assembly, I know that this cylindrical face here and this cylindrical face here need to be axially aligned, and because with the locked in place the SubshapeBinder, the whole geometry of the SubshapeBinder will stay in place and the screw will move. So select first the first cylindrical face, then the second, and apply a axial alignment constraint. Now, if we take a look at our axial alignment, we see that underneath it, apart from having properties that we can tweak, underneath it we have two elements. These two elements represent the faces that we've previously selected, and if we right click, we have some options here like offset element that will be really helpful, flip element, or flip part. The use of these options will become really evident going ahead with our assembly, but we have at our disposal all the tools necessary to create really complex assemblies. So let's go ahead. Now, it is always a good idea to take a look at the report view. In here, the solver will report degrees of freedom or redundant constraints or other important messages. At the moment, we have 2 degrees of freedom left in our assembly, and these are a rotational degree of freedom and a axial degree of freedom. If, for example, I select inside my assembly the link screw, and by pressing AA on the keyboard to bring up the mover tool, we can see that we have a linear movement degree of freedom and also a rotational degree of freedom. Ctrl Z to undo our movement, escape to dismiss the tool, and let's go ahead with our assembly. I will bring in now the BK12 pillow block, so select it, TD on the keyboard, we will bring it inside our assembly container, select it, AA on the keyboard to bring up the mover tool, and we will place it roughly where it needs to be to help the solver place it in its correct position. Also, if you press Ctrl Shift Space, we will toggle off the transparency of the geometry. Let's roughly place it where it needs to be. Now, to place this pillow block, I will use one of the least taxing computationally constraints, and this is the attachment constraint. So, to correctly place the pillow block, I will select this edge here and this edge on the pillow block and apply a attachment constraint. The pillow block has moved into position, and luckily we have no strange rotation of the geometry. Again, looking at our report view, we have 2 degrees of freedom left, one rotational and one axial. Because I know that I want my pillow block to stay in place and not rotate into the assembly, I will apply to it a constraint that will remove its rotational degree of freedom. So to do this, I will select this edge on the pillow block and perhaps this edge on the SubshapeBinder that it is fixed in place, and I will apply a perpendicular constraint. Report view, we have only 1 degree of freedom left, and this degree of freedom is the axial movement degree of freedom. Now, quick tip, if I select my Z-axis components assembly and press the left arrow 3 times, this will collapse all the entries in the tree view, and it will be easier to follow what we are doing. The next component that I want to bring in is the BF12 pillow block, so I will select it, TD on the keyboard to begin dragging. I will drag it inside the assembly and it will be placed inside the parts 3 branch. Select it, AA on the keyboard to bring in the mover tool, and let's move it roughly in place. Escape. I will apply the same attachment constraint, so I will select this edge here on the model and this edge here on the pillow block and apply the attachment constraint. The next geometry that I want to bring into the mix is the belt and pulley assembly, so I will select it, TD on the keyboard, drag it inside our assembly, select it, AA to move it, and let's roughly place it where it needs to be. Again, my constraint of choice in this case is the attachment constraint, so I will select that edge and this edge on the pulley attachment, and the solver will bring the geometry in its place. Notice how the constraints branch of the tree gets populated with the various constraints that we've set it up for our assembly. It is always a good idea to rename them to have an idea at a later time of what they tie to. For example, if I choose this axial alignment and I rename it, we can call this screw to nut. The second one we can rename it BF12 to screw, and so on. For time constraints, I will not do it here, but it is always a good idea to have a reference at a later time of what the constraints actually do inside the assembly, if modifications needs to be done. Okay, so the next element that I want to bring in is the stepper motor, so I will select it, TD on the keyboard to begin dragging. I will bring it inside our assembly, select it, AA on the keyboard for the mover tool, and let's roughly place it where it needs to be. I will rotate this here like this, and let's see what we need to do with this stepper motor. I know that the stepper motor's shaft needs to be axially aligned with this pulley here, and I also know that this surface here needs to be coplanar with this surface here on the pillow block. So let's start by axially align the motor. I will select this cylindrical face here and this cylindrical face here, and I will apply an axial alignment constraint. Instinctively, we could think that if I select this face here and this face here, and I will apply a plane alignment constraint, has solved our need to have 2 coplanar faces. But if we take a look at our report view, we see this message of redundant constraints. This error message is not fatal, but it is better to be avoided, at least until the later stages of our assembly. The redundant constraints lays in the fact that we have a vertical constraint, sort of say set it up by the axial constraint, and also another vertical constraint set it up by the coplanarity of the 2 faces. So I will undo my plane alignment constraint. So Ctrl Z on the keyboard, the plane alignment constraint has disappeared, and I will do it a little bit different. I will select the face here, and I will select only one point on the pillow block, and the constraint that we need is the point on plane constraint. We have an error message. Perhaps we need to select it in a different order. Let's try again. Okay, so we've obtained the same result, but we have 2 degrees of freedom and no solver error messages. We have the linear movement degree of freedom and the rotational degree of freedom of the stepper motor. Again, to lock the stepper motor in place, I will select this edge here and this edge here, and I will apply a perpendicular constraint. Solver messages. We have only 1 degree of freedom left. Let's see what we have left to bring in into the assembly. I will bring in the linear rail, so select it in the components subfolder, TD on the keyboard, and bring it inside our assembly. Because I need 2 of them, I will select the linear rail geometry, and in the properties field I will set the element count to 2. This will create another branch underneath it with 2 links, and these 2 links are essentially clones of our geometry. I will select the first one, AA on the keyboard for the mover tool, bring it roughly in place. The same with the other one, AA on the keyboard, move it in roughly in place, and let's start constraining. I know that this cylindrical face here and this cylindrical face here needs to be coaxial, and we have an error. Control Z. Let's do it differently. Let's select this one here and this one here. I just inverted the order of selection, and let's try again. Okay, and we are pretty much okay. I will select this one here and this one here, and I will apply a axial constraint. As you can see, the solver has moved them slightly rotated, and the solver is not wrong in this case. So what I know is that, for example, this edge here and this edge here needs to be perpendicular, and the same with the other linear rail. So this edge here and this edge here needs to be perpendicular, and we've correctly aligned our linear rails. One measurement that I know that I need to have is to have this surface of the linear rail placed 10 millimeters above the pillow block. In order to do this, I will select this vertex here on the linear rail and this surface, and I will apply a point on plane constraint. The same with this vertex here and this surface here, point on plane constraint. And if we take a look from the front, they are placed exactly as we've told them so, a point on plane constraint. But I want the point to be offsetted by 10 millimeters. We have 2 constraints here. I will expand them. I will select the first element of the 2 constraints, and this first element will be the vertex. As you can see, selected here and here. I will go into the properties in the offset position, and I will offset it by minus 10 millimeters. Okay, so now if we test our assembly, if we select whatever element on the assembly and try to move it with the mover tool, we can see that we have only 1 degree of freedom left, and this is a axial degree of freedom. But in the context of our tutorial, we need to have the position of the linear rails to be symmetric to the position of the pillow blocks, because we need to model in place the various components. In order to do this, I will select this face on the SubshapeBinder, and I will create a work plane. This work plane is positioned under the Part1 branch. I can select it and transform it. I will rotate the work plane, escape to dismiss the tool, and to make the pillow blocks symmetric to this surface here, I will select this vertex here on the one of the linear rails, this vertex here, then the work plane, and I will use this point symmetric constraint. If nothing happens, let's try to quickly solve the assembly, and if we take a look from the front, the linear rails are placed symmetric in respect to the work plane. let's see our whole assembly. And again, in the context of our tutorial, we need to roughly place in space the spindle. So I will select it, TD on the keyboard to begin dragging. I will throw it inside the assembly, select it, AA on the keyboard to roughly move it in place. Okay, so if we take a look here, what I know is that I will model in context the sheet metal, the 3mm thick sheet metal that will form the Z-axis. So the spindle will need to be placed 3mm away from this surface of the linear rail. Also, I would like that this surface here from the spindle, I would like it to be coplanar with the 3mm distant sheet metal surface, 3mm distant from this surface of the pillow block. So bear with me, but we will need to take some measurements to do this. A good candidate for attaching the spindle to our assembly would be this circle here. So I will select it. I will select this circular edge here, and I will apply a attachment constraint. Now, to place the spindle in place, we will need to take some measurements, and I will hide for a second the spindle, and I will measure the distance that we have from this vertex here to this vertex here on the linear rail. I will move to the part design workbench for a second. With the two vertices selected, I will enable the measurement tool. And if we take a look, let's do one thing. Measure, clear all the dimensions, select this vertex here and this vertex here. And as a distance, we can see that we have 30mm. Move to the assembly3 workbench again. Let's close this dialog, unhide the spindle, select the last attachment constraint, select the second element, and we lack another measurement tool. So back to the part design workbench, enable the measurement tool. I will select this vertex here and this vertex here, and we have 48mm. Close assembly3. Select the second element, and now I know that I need to offset this element by 30mm plus 48mm, which is the distance from the center of the spindle to this backplate, plus 3mm of material of the frame that we will later model. I can right click on this element, select offset element, and I will move it the other way. Escape. Now let's just be careful what we are selecting. I will select this element, y-axis field, and the position is minus 30mm minus 48 minus 3mm of the material thickness. And let's take a look from the side. We have placed the spindle where it needs to be. Also, what I need to know is the dimension. So let's move to the part design workbench, enable the measurement tool. I will clear the previously measured distances, and I know that I need to know the vertical distance between this vertex here and perhaps this vertex here, and it is 28mm. Close. Again, move to the assembly3 workbench, select the element. I will offset it. Okay. Be careful of which element you select, and in the Z direction, to be precise, 28mm, minus 28mm. Let's take a look from the side, and this way we have placed in space the spindle also. So this is it for the first part of the tutorial, where we have assembled our components. In the next part, we will start to model in context the frame of the Z-axis. Thank you for staying till the end, and I'll see you really soon.